Bismillahirrahmanirrahim. Assalamu alaikum everyone. So today this lecture is about chronoabsorptometry, and as you can see from the name and as we actually talked about the same in the last lecture, this technique used the same input as was used before in the two techniques, that is in chronocoulometry and chronoamperometry. That is, the input used in this technique is the potential step which is used. However, the response that is measured is now actually make available some additional information. As clear from the name, absorptometry, this technique involves some reactions which are affected by light, and therefore the electrodes which are used in this technique are optically transparent, that is, the light can pass through them, and due to the effect of light certain reactions are taking place which are recorded and give us some important information. Now these type of reactions can actually involve some very important applications such as solar cells, and this type of techniques developed into in its own type of studies, which we will see at the end of the lecture. So to start with, we will just look at some important points, that is about the chronoabsorptometry. And as we can see over here, chronoabsorptometry is the study in which the potential step excitations are combined with UV visible absorbance measurements and therefore are termed as chronoabsorptometry. So the electrodes which are used over here are typically consisting of thin films of conductive material such as platinum, gold, carbon, or a semiconductor such as doped tin oxide, that is deposited on a glass or quartz substrate. So if you are working in the visible region, then you are looking at glass that is deposited on the glass, and if you are working in UV as well as visible region, then you are looking at a quartz substrate for the same purpose. So in addition to that, miniature metal screens, mini grid electrodes in which the presence of very small hole can make it transparent are also used. Now you can see some electrodes over here, different types, which are used in spectroelectrochemical techniques, which actually involve this chronoabsorptometry. So now here you see an OT, that is the optically transparent electrode, and the light is passing through like this because the electrode is transparent. Here the light is deflected from the electrode. Here the light is coming into the solution and then going back after reflecting from the electrode surface, and this one gives a different type of scenario where the light is passing through. That is, you see transmission, internal reflectance, specular reflectance, and then the parallel passage of the incident light. Now the same can be seen over here, which is a more enhanced version of the same thing. That is, the light source is coming through here, passing through the transparent material, and then it is reflected back from the electrode and now detected by a detector. Obviously this part consists of a solution where the electrode is present over here. Now again the electrode is present over here and the light source is here, and it is passing through the solution and then detected over here. Again the light source over here and the light source over here. So there are detectors over here and here, two detectors are present. So you can see that these type of techniques have multiple ways of detection, and then multiple ways of looking at the solutions in which the electrochemical reaction is taking place. So similarly, there are other electrodes like the one with the hole inside, that is the optically transparent screen printed electrodes, where working electrode is made of ITO, P dot, gold or carbon. Now the details of this will be provided in the link. You can actually study that in detail to understand that what is a P dot and what is ITO and where they are actually employed. Now these are some of the actual electrodes that are being used by different systems, electrochemical systems. Now the one you see over here is used by the system Spectroelectrochemical system given by Asad, and this one is the one which is used by Spectroelectrochemical system of Pine Research. And you can see that again this is apparently a quartz or a glass electrode through which the light can pass. The electrode or the electrochemical connections are present over here, and then there is also a connection for gas, and this make the things very clear that how the electrical part and the optical part are going to do. Obviously this is actually being inserted into a spectrophotometer, and this part is connected to electrical component. Similar is the situation over here. You see that here is a hole from which the light beam will be passing, and then it will be detected somewhere, and you can see that the solution can be put over here and the electrical connection will be made at this point. So again you can see more of them if you follow these links. Now coming to the response that we see over here and the signal that is provided, you can check that over here. As is clear in the diagram, the excitation signal is for double potential step which is provided over here, and the response is noted in terms of absorbance over time, that is whatever is happening to the absorbance. So it means that a certain type of arrangement has to be made to incorporate the effect of absorbance in the system. So if you look closely, for absorbance we know that the law which is applied is Beer's law, that is which give A is equal to epsilon BC, and in this equation we have A as absorbance and epsilon is the molar extinction coefficient, C is the concentration, and B is the path length. So in this situation the condition is the continuous increase in the thickness of the diffusion layer, which is the optical cell, and the fact that the concentration of the absorbing species is not homogeneous within this layer can actually create some changes in the equation. So to accommodate that, we need to incorporate some effects over here. So for that purpose we know that once the light is passing, since the oxidation reduction, that is the reaction of in which the oxidized species is converted to reduced species will be taking place, and when it takes place there will be increase in the thickness of the diffuse layer which is present in the optical cell. So the concentration of the absorbing species will not be homogeneous and will be changing. Due to that reason, here is what we write, that is absorbance at any time t is equal to the molar extinction coefficient of the reduced species which is being formed after reaction has been started, that is the oxidized species being converted into reduced species. So in other words, the formation of the reduced species is giving us information about the concentration of the oxidized species also. So we put the integral over here from 0 to infinity, and then concentration of reduced species at any time t and distance x, and substitute the diffusion equation that describes the behavior of the concentration of reduced species. We get from integral this value over here, which include the value of the diffusion constant and as well as time. So using that equation, which is just written, we can calculate the absorbance at any time t. So in this equation we have certain parameters which are present over here. One is this parameter over here, that is this parameter over here, and this gives us the molar concentration of the oxidized species, because as I said earlier that when the concentration of reduced species is known, that is it can be written in the form of oxidized species, because the formation of reduced species give us an idea about how much of the oxidized species have been converted. And d underscore o, it give us, d subscript o give us an information about the diffusion coefficient of the oxidized species, and time is obviously given in seconds. Now again we should emphasize that the diffusion coefficient which is given in this equation are for oxidized species and not for reduced species. Although we are monitoring the reduced species, but as again we should remember that the changes in concentration or the formation of reduced species is telling us that how much of the oxidized species being converted which was present in the solution initially. So in that way we can actually know that how much of the oxidized species is present. So in Chronoabsortometry we optically integrate the amount of reduced species present at any time t in accordance with Beer's law, and in chronocoulometry integrate the amount of reduced species that has been generated at any time by integrating the current required. So we are looking here at absorbance, and there we were looking at the integration of current. So that is the main difference between the absorptometry and coulometry which is taking place. Now Chronoabsortometry is useful for the study of homogeneous chemical reactions that involve an electrogenerated species. For example, you can see over here that the reduced species being electrogenerated from oxidized species, that is this one is the reaction which is taking place at the electrode, and this is followed by a reaction which is chemically taking place. For example, consider the situation in which an additional species Z is also present in solution and is capable of rapid homogeneous chemical reaction with R at a rate characterized by the second order rate constant K to form product P. So until or unless this reactive species R, which is reduced species R, is formed, this reaction cannot take place, which is going to take place chemically. So first the formation of R will take place, and later on the formation of the product after R react with another species Z will take place. Now in this case the electrogenerated R will encounter Z as it diffuses away from the electrode and will react to form the product. This diffusional mixing of two reactants, that is R and Z, is the basis for Chronoabsortometry and some other electrochemical techniques and make it a kinetic method. The homogeneous chemical reaction of R will perturb its accumulation by a magnitude that is proportional both to the rate constant K and to the concentration of Z, which is already present in the solution and waiting for the formation of the reduced species R, which is acting as one of the reactants. So the influence of this perturbation is apparent from the concentration distance profiles for R, and which are illustrated for the rate constant of 10 raised power 7 liter per mole per second and will be given here. So the same you see over here in this figure. What is happening, that is O and Z are initially present, but first the formation of R take place and then this R react with Z for the formation of the product, because initially the product is 0. So obviously the product will be at high concentration over here, and as the reaction proceeds the concentration of product will continue to increase as with the formation of the reduced species R. Now the same is observed sequentially in this figure. So here is another important result, another type of result that is actually explaining similar kind of situation. So if we look at this figure, so what we get is that what is happening in different cases, that is absorbance time curve for transmission spectroelectrochemistry, EC mechanism for rate constant K of 0, 10 raised power 5, 10 raised power 6 and 10 raised power 7 liter per mole per second molar absorptivity. So R is monitored optically, that is the concentration of reduced species, while the diffusion constant of the oxidized species is 10 raised power minus 6 centimeter square per second. Epsilon molar absorptivity is 10 raised power 4 liter per mole per centimeter. Concentrations of A and Z is 1 millimole over here. So starting from A, you can see that how it is reducing over here. Now this AT, that is the absorbance versus time curve, clearly shows that the absorbance response is very much sensitive to the magnitude of the rate constants, which are given over here, that is 0, 10 raised power 5, 10 raised power 6 and 10 raised power 7 liter per mole second. And for A it is largest, then for B for A it is 0, then for B it is increasing, for C more, and for D it is the largest. So it shows that a rate constant can be determined by fitting an experimental curve to calculated curves, or by fitting to a dimensionless curve. And this is demonstrated in several homogeneous reactions which can be actually looked from in literature. Now the transparency of electrode enables many things. It actually helps us to record the electrogenerated species when it is forming, and at the same time it helps us to record the rate. So you can see that in an experimental setup you have a light source, then a cell, then this cell is simultaneously connected to a potentiostat and a spectrometer. So you are actually noting both the responses simultaneously, that is the electrochemical response and the synchronization with the spectroscopic response, and all of this is termed as spectroelectrochemistry, in which if you are applying this step potential, then actually you are looking at chronoabsorptometry. Now, what you need to do is to explore the recent trends in research related to spectroelectrochemistry. See that how the papers are recently appeared. Actually, those papers are covering many things about the solar cells and other energy materials. And for example, it is also covering things about biosensors and sensors and other things. And you need to check how technology expanded the realms of possibilities and limits of analysis in spectroelectrochemistry for detection. And then you can study these papers which are given over here. And we stop for now, and we will meet in another video and also on lectures. Thank you.